Well, hi everyone. My name is Santos Takal. I'm currently a first year master student here at University of Connecticut, working under the supervision of Professor Ramesh Molla. I'm working on this project called Structural Health Monitoring of Old Railroad Bridges in Connecticut, primarily focusing on material characterization part. Having said that, let me jump into my presentation today. The topic of my presentation is tensile properties of two old railroad steel bridges in Connecticut. So let me start my presentation with the introduction. Today I'm presenting the tensile results from two of the railroad bridges in Connecticut. The bridge on the left is the Devon Bridge, while the bridge on the right is the Costco Bridge. Um, These two bridges were built using this Yastium A7 steel. This Yastium A7 steel has the yield stress of 33,000 psi, while the steel we use nowadays is Yastium A36. This is the steel we use nowadays, which has the yield stress of 36,000 psi. So the steel um, that was used to build these two bridges as the yield stress of 3,000 less than this Yastium A36 steel. So as an engineer, we might be very curious to understand how this particular material, how these two particular bridges built in this 19th century are behaving today. So my primary objective is to present the tensile properties of the critical members from the Devon and the Costco bridge obtained from the tensile test. Before I jump into the methodology, I would like to give a brief introduction about these two bridges. The first one on the left, the Devon bridges, is located over the lower Housatonic River between Milford and Stafford. This bridge was built in 1906 by American Bridge Company and owned by Connecticut Department of Transportation now. The sample material from the bridge was from the Stringer angle. Similarly, the bridge on the right is the Costco Bridge, which is located over the Mianas River in Greenwich. This bridge was built in 1904 and owned by Connecticut Department of Transportation, and the sample material was collected from the bracing members of the adjacent pedestrian bridge. Well, with that, let me jump into the methodology. Um, so, the specimens collected from these two bridges were fabricated uh, and the dog bone shape specimens with the gauge length, width, and thickness of 2 inch, 0.5 inch, and 0.29 inch respectively were prepared according to STM E8. So the gauge length A denoted by A in this sample is 2 inch, and the width denoted by C is 0.5 inch, and the thickness is 0.29 inch. And those prepared samples were tested using this particular machine from Instron called Instron 5869. Okay, now let's jump into the results section right here. The results from one of the specimen from this bridge is presented in table 1. The results for specimen 2 from Costco bridge shows that the yield stress of 223 megapascal at yield strain of 0.0012, so that's the 0.12% yield strain. Similarly, the tensile stress is 368 megapascal. Um, Similarly, for the Devon bridge, uh, the results for the specimen 3 are presented here. Um, the result shows that the yield stress is 202 megapascal at the yield strain of 0.11%. The stress strain plot of this uh, corresponding samples are presented in figure 4. The one on the right is the stress strain plot from the Devon bridge, and the one on the left is the stress strain plot from the Koskov bridge. So these results obtained from the testing are compared um, with the uh, with the value defined in STM A7 1939 standard and the results published on Frieze laboratory report. The report defines yield strain at 0.112%, so we are very close with the results that are documented on this particular report. Similarly, this STM A7 1939 defines yield stress at 33,000 psi, that means about 228 MPa. So if we look at the yield stress value, we are very close to what they actually define. So our results are very relatable with what ASTM A7 1939 specifies and what this report from Frieze laboratory um, recorded. So we can say our results are very consistent. So we can conclude that the material has maintained their elastic yielding, plastic deformation, and strength hardening characteristics. I mean, these are just the preliminary test. We still have many more tests coming on after the completion of our testing. We can we can say how. I'm sorry. I mean, after the completion of test, we can say more clearly how these materials um, are behaving now. So, having said that, I would like to conclude my presentation, and before I conclude, would like to acknowledge the Transportation Infrastructure Durability Center um, for the grant for this project, and similarly, we would like to thank to Metro North Railroad and Connecticut Department of Transportation for their support throughout this research. Um, Thank you.